The deterioration of old sewer lines has plagued the country for years. Today, the question is how to quickly and cost-effectively repair these sewers without digging up streets or private properties. The answer is to restore new life to them by inserting modern, corrosion-resistant liner pipe into the existing sewer lines by a method called sliplining. This is a view of a typical sliplining project. You're looking at 36-inch diameter PVC slipliner pipe delivered to the job site to be inserted into an existing 42-inch diameter concrete sanitary sewer line that had deteriorated. To accomplish this task, insertion pits are constructed to provide access into the old sewer for the insertion of the liner pipe. Note that the top half of the existing pipe has been removed so the liner pipe can be inserted into the old sewer. The slipline pipe is obviously smaller in diameter than the old pipe. But polyethylene, PVC, and fiberglass liner pipes have smoother surfaces, so their capacities are just about equal to the old. Now, let's make short work of the sliplining. Now that's done, you can see that the new liner pipe has been inserted into the old pipe. But the total slipline process is only half finished. There now exists a void between the liner and the old pipe. That void must be completely filled with a suitable grout material. The grout material must flow like water when mixed, stabilize the liner pipe, prevent collapse of the old pipe, withstand the pressures of groundwater and soil compression, and physically resist change. The grout material that has been used in the past was concrete piped into the void as a cement slurry. But ordinary cement slurry is heavy, and that creates a problem. Ordinary cement slurry has a density of about 110 pounds per cubic foot, and that makes it a lot heavier than water, which is 62.3 pounds per cubic foot. So even though the liner may be filled with water during grouting, the ordinary cement slurry, being heavier than the water in the liner pipe, lifts the liner pipe to the top of the old pipe. That's right. The inner pipe floats to the top of the heavy cement slurry, destroying the pipe's design slope, its gradient, so the wastewater is no longer running downhill. But that's not the only problem. There's the natural heat generated by hydration during the curing stage of the concrete. During the hydration of ordinary cement slurry, temperatures typically range between 180 and 200 degrees Fahrenheit, substantially more than the heat distortion temperatures of 140 degrees for plastic liner pipe and 172 degrees for fiberglass. But we have a better way of doing it. With the material and method for annular space grouting adopted in the California Green Book standard specifications, cellular concrete grout. Here's how we do it. We begin with a ready-mix truck half full of Portland cement slurry, batched in accordance with our mix design. Then we generate a foaming agent. You can see its consistency. And we pump the foaming agent into the concrete mixer for blending into the slurry. The foams and trapped microscopic air bubbles create a grout that is approximately 50% entrapped air, and now weighs just half as much as ordinary cement grout. Well, that's the idea. Now let's do it. This is the ready-mix truck that's delivering cement slurry to the job site. The other equipment you see is support equipment for the grouting operation. Here we're taking a sample of the slurry from the ready-mix truck. The first step in grout quality control is weighing the cement slurry sample, contained in a calibrated container, on a precision laboratory scale to determine its precise specific gravity. Once the slurry weight has been determined, a calculated amount of foaming agent is blended into the slurry in the ready-mix truck. This will reduce the grout density to a specific gravity lower than water. The second step in quality control, weighing a sample of cellular concrete grout after foaming to confirm that the desired calculated specific gravity of less than water has been achieved. This means that the liner pipe, when filled with water, will not float and will maintain its grade throughout the grouting process and forever after. The third step in quality control, determining the viscosity or fluidity of the grout by using a flow cone. First, the flow cone is calibrated by timing the flow rate of water through the cone. After calibration, the flow rate of the foamed cellular concrete grout is timed to confirm its proper viscosity. The apparent grout viscosity shall not exceed 18 seconds. With these quality control steps completed, foamed grout is ready for pumping into the annular void of the relined sewer. Grout is discharged into the concrete pump hopper to begin this task. Here is the grout hose with a precision oil-filled pressure gauge that is connected to the grout injection pipe, which has been inserted through a watertight bulkhead into the annular void of the slipline sewer. During the pumping procedure, the grout pump operator constantly monitors injection pressure to ensure that it does not exceed design limits of liner pipe. Samples of the grout are ladled into molds 3 inches in diameter and 6 inches high for delivery to the testing laboratory for cure and compression strength tests. In the downstream manhole, water is flowing from the vent pipe of the line which is being grouted. This water is being displaced from the annular void of the relined sewer by the viscous grout mass. The annular void has been filled, and grout, instead of water, is flowing from the vent pipe of the line. The final stage of quality control, when the viscosity of the discharged grout seems to match that of the grout being pumped, a sample is taken to the scales and weighed to confirm that the specific gravity of the discharged grout matches that of the injected grout. Cured samples of the samples of cellular grout are prepared in the testing laboratory for compressive strength tests. Samples are tested in a precision compressive test machine. Our specifications call for a minimum penetration resistance of 100 psi in 24 hours, minimum compressive strength of 200 psi in 7 days, and 300 psi in 28 days. You've seen the disadvantages of using heavy grout to fill the annular void. Now let's look at how it's done with lightweight, foam-entrained cellular concrete grout. We begin here and begin to pump in the cellular concrete grout. Note that the wastewater-filled slipline pipe stays on the bottom of the old concrete pipe. No great pressure was involved, and the heat of hydration was 110 to 120 degrees Fahrenheit, well below the heat distortion temperatures of 140 and 171 Fahrenheit for plastic and fiberglass liners, and far below the 180 to 200 degrees Fahrenheit developed by heavy grout. More than that, this is an engineered injection of a material, low-density cellular concrete, that greatly improves the structure and the future of the slipline pipe and its host. While cellular grout is light in weight, low density, and very fluid, when the cellular concrete sets, it can be just about as strong as you want to make it. So whenever there's sliplining and a need for grouting, think of low-density cellular concrete grout and us, Southeast Pipe Survey.